Okay, this is 2.1, determining average rates of change. Introduction to chapter 2. This is the very beginning of calculus. This is kind of where it all starts. It starts off actually quite simple. The average rate of change is really just kind of another word for slope between 2 points. Okay? They'll define it here. It's a relation, the change in the quantity given by the dependent variable change of y divided by the corresponding change in the quantity represented the independent variable change of x for a function y equals f at x, the average rate of change of the interval. So this is kind of a big description of slope of 2 points, right? So it should be very familiar. Okay, so it's kind of just like slope. It says the goal is to calculate and interpret the average rate of change on an interval of the independent variable. So it gives us a bacteria problem here. So as time increase from 0 to 2 hours, the number of bacteria increase. Okay, so this is a very typical exponential function. You would have seen this probably in grade 11 as well, this bacteria growth problem. So what happens is, as the bacteria replicate, there's more and more of them to then replicate further. So they get this kind of exponential growth happening. All right, so that should be pretty obvious. During which 2-hour interval did the bacteria population grow the fastest? So just by kind of roughly knowing that this is an exponential growth pattern, you're going to see something like this, right? Okay, where this is time and this is our number of bacteria. So right away with any exponential graph, we know that the time in which they increase the most is going to be the last 2-hour interval. Okay, because that's the time at which the slope is the greatest, right? The slope is kind of going like this, right? If we think of it in straight lines. Okay? So they go through the process of creating a table of values, which is fine. They're looking at the interval between 0 and 2. So they take this value, they minus this value, take this value and minus this value, and they get our change in T, which is 2. And then they get our change in bacteria, which is 1122 minus 850. So 272. Okay? And then they get the slope of that particular line. So if they go from 2 hours here and 0 hours here, they're taking this point and they're really just calculating the slope. Okay, and the slope is our average rate of change of bacteria, okay, which is rise over run, or y over x. Any questions there? It says calculate the average rate of change in the dependent variable for each 2-hour interval, divide the change in the number of bacteria by the corresponding change in time. So again, they're just finding kind of rise over run. We're getting away from slope on purpose, actually, so I'm not going to kind of come back to it after this. I just wanted to point out how similar it is to average rate of change, which is slope. Reason why is we're going to go into instantaneous rate of change, which will be quite different. So it says the greatest change in the bacteria population occurred during the last 2 hours. Okay, so that's evidence. This is our slope of our last line here between the interval of 10 hours and 8 hours. Okay? Any questions on this page? Yeah.
You know how it's an exponential growth, it's kind of like that, right? So if you wouldn't it be like that and then like that and like it's not like a one smooth line.
Right. So you're saying that wouldn't it look like?
Yeah.
Yeah, so if you were to plot these particular points, right, it would look like this. But if you think about it, they're not just reproducing on each 2-hour interval, right? The bacteria is reproducing throughout. So it is actually, it's all real numbers if you think about it, of time, right? Because there's 1 hour, there's 1 hour and a half. There's all the intervals between 0 and 2 hours. So these are not just points, right? These are points in a series of multiple points, which would create this kind of smooth line, okay? But you're right, given the data we have, we do only have these points right now, but we can make that assumption based on time not being only existing on every 2 hours. Okay? Any other questions with this one? Okay, next one is they plot a graph. So here's what Ramon was talking about actually. There's actually straight lines here we can see between each point. But you can see it's already quite evident that it's approximating an exponential curve here. It says create a scatter plot using the data and then draw a secant line that passes through each pair of data points for each 2-hour interval. So a secant line, it's important that we understand what that means. It's a line that passes through 2 points on the graph of a relation. So a relation or a function, we have 2 points on it. That secant line is going to pass through those 2 points. So secant line, it connects 2 points on the graph. Connects 2 points on the graph. Okay. Later we're going to start talking about the tangent line, which actually is just 1 point on the graph. Okay, and that's when we get to the basis of calculus. Okay, but for now, the secant line, I'm going to draw it a little bit blown up here. So what'll happen with a secant line is a lot of time, or all the time, it'll cross on the inside of the graph. Okay, you can't really see that here, but that's what's happening. That line actually goes on the inside of that function line. Okay, so on a curve like that, it goes on the inside. On a curve like that, you have 2 points still going to go on the inside.
So what if it was a different parent function?
So this is your secant line. Yeah, it's always going to go on the inside of a curve. So if you had a different parent function, like y equals root x, and you connected 2 points, you're still going to go on the inside. Okay? If you had y equals 1 over x, and you draw a secant line at any point, it's still going to go on the inside. Okay? Alright, so next it says calculate the slope of each secant line to verify. So what we're doing here, 1, 2, 3, is the exact same thing that we did in the table. So we're just getting the slopes. So see 136, 136, 179, 179. These are just the slopes of the secant lines. Alright? So again, it says it concludes the greatest change of population occurs in the secant in the last 2-hour interval. Okay, it says why is the average rate of change of the bacteria population positive on each interval, and what does this mean? How is this represented by the secant lines on the graph of the data? What does this mean? The slopes are positive. What does it mean? Yeah.
It means it's always increasing.
Yeah, exactly. It means that the population growth is increasing. So the rate at which it's growing is increasing. It's always positive. Good. How is calculating an average rate of change like calculating the slope of a secant line? It's the same thing, right? Is the dependent values divided by the corresponding change in the independent values? It's just like rise over run. Why does rate of change have units even though slope does not? Anybody know? Yep.
Because average rate of change is actually dealing with the concept within a question, where slope is just part of the equation line.
Exactly. Yeah, that's a perfect answer. Yeah, so slope is like an abstract kind of concept. It's typically just dealing with x and y values just as units, whereas the average rate of change is dealing with very specific values. In this case, number of bacteria versus time. Okay, that's why we give it units. Okay? You can't give slope units if it's just a number over a number. By definition, there's no units to those x and y values. So when you're learning slope in grade 9, it doesn't have any units at that point. Why is the rate of change in the bacteria population not a constant? Anybody know? Yeah.
When you mean constant, like always the same.
Yeah.
Well, it's because there's like more of them. Like if one bacteria can have 2 bacteria, that 2 bacteria each could have like 2 or 3.
Yeah, that's exactly right. Everybody hear that? Basically, as they reproduce, then more can reproduce, and that's why it's not constant. Okay, because they're all reproducing. Okay, example 2. Reasoning about the average rates of change in linear relationships. Sarah rents a car from a rental company. She's charged $35 a day plus a fee of 15 cents per kilometer for the distances she drives each day. The equation C at D is equal to 0.15 D plus 35 can be used to calculate her daily cost to rent the car, where C at D is her daily cost in dollars and D is the daily distance she drives in kilometers. So we're given a function of cost related to the distance that she drives. Discuss the average rate of change of her daily cost in relation to the distance she drives. All right. So we're talking about graphing this particular graph here. So we can see that we've graphed this. It's just a straight line with a y-intercept of 35 and a slope of 0.15. So the relationship's linear, so the rate of change in the daily cost is constant. Okay, we know that because it's this equation of a line. The average rate of change between any 2 points on the graph is always constant. The secant lines that are drawn between any 2 pairs of points on the graph have the same slope. So if I try and draw a secant line between this point and this point, I'm going to get this line. If I draw it between this point and this point, I get the same line. So, very important, the secant line on a straight line is always the same between any 2 points. Pretty self-explanatory, right? Whereas on a curve, if you have these 2 points, you're going to get a different slope than, say, these 2 points. Okay, so on a straight line, you get the same secant line no matter what points you take. Okay, using the distance interval from 0 to 100, we can calculate the average rate of change, or the cost per kilometer driven. All right, so it doesn't matter which point we choose, whether it be 0 and 100 or 100 and 250, we're going to get that same value. That's because it's a straight line.
Why'd you put 100?
Sorry?
Why'd you put 100?
They just chose that arbitrarily. So they just chose this point, 100 here. See? And they found these values, right, by just plugging in x and y. They found these values here just plugging in x and y into this equation. All right? So they're choosing the x values and figuring out the y corresponding values. All right, so the farther she drives each day, the more she will pay to rent the car. However, the rate at which the daily cost increases does not change. For every additional kilometer she drives, her daily cost increases by 15 cents. Any questions about that one? Pretty straightforward. Example 3, using a graph to determine the average rate of change. Andrew drains the water from a hot tub. The tub holds 1,600 liters of water. It takes 2 hours for the water to drain completely. So here's our time, 120 minutes, which is right here. There's no more water in the hot tub. Okay. The volume in liters of water remaining in the tub at various times in T minutes is shown on the table and graph. Okay, so they have a table of values here and a corresponding graph that they plotted based on these values. And these are all given. Okay. Why do you guys think that in the first 40 minutes it drains almost 1,000 liters, and in the last 80 minutes it drains less than that, only 700? Why do you guys think? Why does so much water come out of the hot tub initially when they start draining it? So you got to imagine there's a plug at the bottom. Why doesn't it just come out all at the same rate? Yeah.
the water is heavy at first and then it gets lighter.
Yeah, so because there's so much water on top that's weighing down on the water at the bottom, it's actually pressuring that water to come out. By the time all the water's come out, now there's just a little bit of water left. There's not a lot of weight or pressure pushing down on the water. Okay, so that's why we get this kind of reverse exponential rate of which the water is draining. All right, any questions on that graph? I'm going to slide it over because I think we're going to need it. Oh, we got another one. It's okay. It says calculate the average rate of change in volume during each of the following time intervals. So between 30 and 90, how do I calculate the average rate of change between 30 and 90? Anthony. So I want to get the average rate of change. Anthony, what do you think? Between 30 here and 90, how do I get the average rate of change?
Find the scale line, the secant lines.
No, we don't have to draw the secant lines. You could if you want. Let's see, 30 is there, 90 is there. Your secant line would be here. But we don't need to, right? How do we find it?
Line of festival.
No. It's easy. How do you get the slope between these 2 points?
Or y2 minus y1.
Yeah, exactly. So we're going to take the volume values, which is y, so we have 100 minus 900 over 90 minus 30. Negative 800 over 60.
So do you want to simplify it?
Yeah, I want an answer. And what are the units for this, Kevin?
Liters a minute.
Liters per minute,
Minute, sorry.
right? And why is it negative, Kevin?
Because you're losing water.
Right, because the liters are going down. Okay, because it's decreasing. Any questions on that? How to get the average rate of change? Daniel in the back, how do I get the average rate of change for 60 to 90?
So do the same thing then. You use the 2 points, so you do y2 minus y1,
Mm-hmm.
and then over x2 minus x1, so it would be 400, no, 100 minus 400
Mm-hmm.
over 90 minus 60. And then so that would come out to negative 10.
Good. Okay, so what we see happening as we go higher in the value in time, so from 60 to 30, we're draining at 13 liters per minute. And then as we go from 90 to 60, we're now draining at 10 liters per minute. So the rate at which the water is draining out is slowing down. Okay, and that's for the reason we discussed. The weight of the water no longer pushing out. Okay, so you can see that here. They solve for negative 13.3, negative 10. We'll see the other values now. They solve between 110 and 90. It goes down to negative 4.5. And finally, in the last 10 minutes, they solve here. They're only draining at 1 liter per minute. Negative 1 liter per minute. So really slow. It's just trickling out at that point. The volume of water is decreasing on average at the rate of 1 liters per minute between 110 minutes and 120 minutes. So I hope now this example is kind of the first example that's kind of sees the usefulness of rate of change and slope for specific applications, right? If you can calculate these slopes, you can have a better, you can make estimates about how long you'd have to wait for the hot tub to drain, and you can start to see kind of the practicality of knowing average rates of change. Next question asks, why is the rate of change in volume negative during each of these intervals? We already talked about that. C, does the hot tub drain at a constant rate? Explain. No, we talked about that as well. The reason why it doesn't drain at a constant rate is because of the weight of the water. Finally, the magnitude is the absolute value of a quantity. So let's talk about this. Looking at the slope calculations, the slopes of the red and blue secant lines have a greater magnitude than the slopes of the green and purple secant lines. So it's tough to see here. Red and blue have a greater magnitude than the slopes of the green and purple. Green, I don't see purple. I don't know where purple is.
So last 2 points.
It's the very last. Oh, it's like right there. Yeah, it's right there. The slopes of the secant lines between points over 10-minute interval are smaller in magnitude as time increases. So magnitude is kind of just another word for the absolute value or quantity. So you can see that it's going, it's greater initially and then going down. So the slope value is less. All right, last example. Using an equation to determine the average rate of change. This is obviously my preferred one. I always prefer algebra to any table of values, any graphing. I just find it's going to be more accurate and easier in the end. So it says a rock is tossed upward from a cliff that's 120 above the water. There's the y-intercept 120. The height of the rock above the water is modeled by this, where h is the height in meters and t is the time in seconds. Okay, so there's our pretty stereotypical parabola function. It says calculate the average rate of change in the height during each of the following intervals. So how do we do this now? We don't have a table of value, so we can't take two values and subtract them, and we don't have a graph. So we can't like draw the points and calculate the slope. So how do we do this? Gianluca?
You have to take 2 points.
Yeah?
You have to do delta y over delta x.
Yep. How do I do that? Delta y over delta x. What do I do? So what's delta x, first of all?
It's cheaper than the x.
Yeah, so what is it for ai?
It's 1 take away 0.
Right, 1 minus 0. And then what is delta y?
You have to plug in the 1 and the 0.
Right, you got to plug in these values in here for t. Okay? And the reason we do that is we can find out the y values once we plug them in. Okay, so you can see that here in the solution right here. They take the height, change of height. So they write it in function notation, h at t, where they're plugging in the value of t as 1 and the value of t as 0. And then they just calculate. So they get it as 125. You don't see that here, but what they've done is negative 5, 1 squared plus 10 times 1 plus 120. So we have negative 5 plus 10 is 5 plus 120 is 125. Okay, and then they do the same thing with 0, plugging in 0 into this equation would leave you with just 120. Okay, and then they calculate the average rate of change, or the slope, at those 2 points. Any questions on how all of these were done? They're all straightforward. They're all just plugging in those values into this equation. Any questions there? Okay, B, it says, as the time increases, what do you notice about the average rate of change in height during each 1 second interval? So what do we notice? It's going from here, 5 to negative 5 to negative 15 to negative 25. So the height here initially was increasing. So the stone was going, here's our cliff, and here's our stone. And it was thrown like this. So initially, in this section here, we were going up 5 meters per second. Okay, so our height was going higher, higher, and then after 10 or 2 seconds, already we started going down between 2 and 1. So now this area here, we were going down negative 5 meters per second. And then what happens is, as we know, as a rock falls, it starts to speed up. So then we had negative 15 meters per second. And then finally down here, we had negative 25 meters per second. So that's an actual practical value there, right? That means that the rock is moving 25 meters in a second at the end there. So it's going pretty quickly. It's pretty high cliff. Right? So if it continues at this rate, in 3 seconds, you're going to fall 75 meters. It's obviously going to speed up faster than that still. Any questions about this? So the average rate of change are positive and then negative because the rock's height increases and then decreases. The average rate of change in the height is also changing for each 1 second interval. After 1 second, as time increases, the rock is dropping a greater distance. The magnitude of the average rates of change are increasing. The rock is not falling at a constant rate. It's picking up speed. Finally, describe what the average rate of change means in this situation. It compares a change in distance over an interval of time. The rate of change represents the speed of the rock over the interval. That's because we know speed is equal to distance over time. Okay? The rock is speeding up as it falls. Any questions there? Okay, pretty easy section.
Mr. Mills?
Hi there.
Yes, hi. Could we see Anthony Lee in the office, please?
Sure.
Thank you.
All right, finally in summary, the average rate of change is represented by this equation, very similar to the slope that we're familiar with. There it is in function notation. Okay, get familiar with this equation. It's going to come up next term in calculus quite a lot. Okay, we're going to be looking at that a lot. Graphically, the average rate of change for any function y at f at x over the interval is equivalent to the slope of the secant line passing through the 2 points. Okay, so the same thing, right? We have the same equation here. So you need to know the average rate is change expressed using units of two quantities that are related to each other. Positive average rate of change indicates the quantity represented by the dependent variable is increasing on the specified interval compared with the quantity represented by the independent variable. Okay, all this we know. Negative, the opposite. All linear relations have a constant rate of change. Average rate of change calculations over different intervals of the independent variable given the same result. Okay, these are straight lines. Straight lines give us the same rate of change. Nonlinear relations do not have a constant rate of change. Average rate of change calculations over different intervals of the independent variable give different results. It's kind of redundant what they're saying here, but there it is. Any questions?